Okay, so last time we had some technical problems. After that, I had to rewrote the notes and recorded new videos. Okay, so let me just start from so-called regular singular points. So remember, a point is called ordinary if px is not equal to 0 at that point, and it is called singular if px0 is 0. In general, solutions about a singular point might be quite difficult to obtain, to write down. However, there's a special case, so-called regular singular point. Okay, regular singular point. Around the regular singular point, life is kind of easy compared to an arbitrary singularity. And what's a regular singular point? A regular singular point, x0 is a point where px is 0, but these two limits, so x minus x0 times q over p and x minus x0 squared r over p both exist. If they both exist, then we call that point a regular singular point. And we will see that solutions can be obtained around regular singular points, and we understand more or less what's going on, although not completely. Okay. And I gave one example. Consider, for example, this differential equation. So p is 1 minus x squared, q is minus 2x, and r is 2. They are all analytic functions. The points where px are 0 are the singular points, and in this case, they are just plus minus 1. And we checked whether they are regular or not. So we look at the two limits. Limit as x goes to x0, x minus x0 times q over p. And in that case, this limit is just 1. And we also look at this limit, x minus x0 squared r over p. And this limit turns out to be 0. So both limits exist. Therefore, x0 equals 1 is a regular singular point. Sorry, minus 1 is a regular singular point. Similarly, we checked the other singular point, 1, x equals 1. And we see that, again, both limits exist. One of them is 1, the other one is 0 again. And again, x0 equals 1 is a regular singular point. All right. Now, before we pass solutions about regular singular points, we will cover a topic so-called Euler's equation. And it turns out that actually regular singular points, or the solutions about regular singular points, are kind of generalizations of this Euler's equation and its solutions. And Euler's equation is easy. It's basically a constant coefficient equation after a variable change. So we will first treat, understand Euler's equation, and then we will come back to regular singular points. So let's do that. Okay, so this is section 5.5, Euler's equations. What's an Euler's equation? It's an equation of the form. An equation of the form x squared y double prime plus alpha x y prime plus beta y equals 0, where alpha beta are fixed. Okay, let me take real number. Are fixed real numbers is called an Euler's equation. Okay. So it is basically a constant coefficient equation, but it is not, right? I mean, there are x squared term and x term here. However, we will see that actually after a variable change, this turns out to be an constant coefficient equation. How? So how to solve? Let's see this equation. Well, uh, let's change the independent variable using x equals e to the power t. Okay, so I will replace the independent variable x with the independent variable t using this formula that x equals e to the power t. Let's see what happens. So my function y is a solution is a function of x. Of course, I will write e to the power t inside, so now it will become a function of t. Now let's write the derivatives here. Here derivatives are with respect to x, of course. Let's write down those derivatives in terms of t. How can we do this? You see, dx, dy dx is just, or let's say dt is what? This is just dy dx times dx dt. Well, this is just dy dx, and then dx dt. Dx dt is just e to the power t, right? And what is e to the power t is again x. So this is just x times dy dx. Okay. And what about dy squared dt squared? Well, that is d over dt of dy over dt, right? Second derivative. And what is this? Well, this is just d over dt times derivative of y with respect to t. That is just, we already computed that. Okay, it is just x times dy dx. And what is this derivative? Well, I can write this as follows. This is just derivative of derivative with respect to x times derivative of x with respect to t. Well, let me take the derivative of this expression with respect to x. So derivative of x, which is 1, and then dy dx, plus x times derivative of this with respect to x. Well, that is just d squared y dx squared. And then I have just dx dt. But dx dt were just e to the power t, and that is just x. Okay, so this is just what? X times dy dx plus x squared d squared y dx squared. So we have the following formulas then. Dy dt is just x times dy dx, and d squared y dt squared is just x dy dx plus x squared d squared y dx squared. And from this we see what? Well, I have, you see here I have these terms in the Euler's equation x times dy dx, right? So it is already uh, this gadget. X times dy dx is just dy dt, and x squared dy squared dx squared is just d squared y dt squared minus x times dy dx. Well, that is just d squared y dt squared minus x times dy dx is just dy dt. So the Euler's equation can be written then as, what was the equation? It was this, x squared dy squared dx squared plus alpha x dy dx plus beta y equals 0. And this can be written as what? Instead of x squared dy dx, I will write dy squared dt squared minus dy dt, right? So x squared dy dx squared is just dy squared dt squared minus dy dt plus alpha times x times dy. X times dy is just dy dt plus beta times y. Now this is an equation in y and t. Okay, so let me rewrite again. So here, this time, y is a function of t, and y satisfies the following equation. D squared y dt squared minus or plus alpha minus 1 times dy dt plus beta y equals 0. You see that now it's a constant coefficient equation, which is a constant coefficient equation, and we know how to solve it, right? Okay, how can we solve this equation? We write its characteristic equation, and what is that? It is just r squared plus alpha minus 1 times r plus beta equals 0. And depending on the type of roots we have different kinds of solutions. Let's see what kind of solutions we may have. Case 1 is just, okay, we have r1 greater than r2, two distinct real roots. Okay, now in that case, what are the solutions? Y1 is just e to the power r1t, and y2 is just e to the power r2t, and the general solution is just c1 times y1 plus c2 times y2. Okay, now remember that x was e to the power t. So if I want to write again the solution in terms of x, because my original variable is just x, right, not t. So after I solved this equation and obtain the solution as a function of t, I have to use this substitution again and write down the solution in terms of x. So x is just e to the power t, therefore x to the power r1 is just e to the power r1t, and similarly x to the power r2 is just e to the power r2t. Hence the general solution is what then? It is just c1 times e to the power r1 plus c2 times e to the power r2. Okay. So what I have to do, I have to write down the characteristic equation for the given Euler's equation, obtain the roots, and write down the solution. Let's do the other cases also. Example, case 2. I have R1 equals R2, okay, double root. In that case, we know that one solution is e to the power R1t, and the second solution is just t times e to the power R1t. Let's say this is equal to R, double root. Okay, and if I write these again in terms of x, this is just e to x to the power r. And what is t? Well, x was e to the power t, therefore t is just ln x, okay? So what we get is just ln x. Okay. Actually here x is already positive, right? Because x is e to the power t, so I don't need even this thing. Okay. What else? Okay. Case 3. Complex roots. Non-real roots. Well, in that case, the solutions were y1 e to the power lambda t times cosine mu t, and y2 is e to the power lambda t sine mu t. And remember what was t? T was ln x. Therefore, e to the power lambda t is just e to the power lambda t is just x to the power lambda. Okay. And t is ln x, therefore y1 is just x to the power lambda times cosine mu times ln t, or x to the power lambda times cosine ln t to the power mu, and y2 is just the same thing. This time I have just sine, right? Mu times ln t, not ln t, ln x, I am sorry, ln x. So this is just x to the power lambda times sine ln sine x to the power mu. Okay, so the solution would be just x to the power lambda parenthesis c1 times cosine okay, let me write mu times ln x plus c2 sine mu times ln x. So these are the solutions. Let me just do some examples. Okay, now solve the following equations. One is just, okay, x squared plus 3x e to 3x not x. Okay, x squared y double prime plus 3x y prime plus okay, y equals 0. Well, this is an Euler's equation, right? Euler's equation with alpha equals 3 and beta equals 1. So what is the characteristic equation? In this case, once you make the variable change, okay. Actually, in this case, this equation, characteristic equation, will be called indicial equation. But let me just talk about it later. So what was the equation? It is just r squared alpha minus 1r plus beta. So this is r squared plus alpha minus 1r plus beta equals 0. So we get r squared plus 2r plus 1 equals 0. So it is r plus 1 squared is 0. So we have r1 equals r2 equals r, which is minus 1. So we have double root case. Therefore, the solution would be just, what was the solution in case of double roots? So I have just this. Okay, so general solution was C1 times Y1 plus C2 times Y2. So it is x to the power R parenthesis C1 plus C2 times ln x. Okay, this is just x to the power R, and this is Y2, which is x to the power R times ln x. Okay, so it is just x to the power R, x to the power R times C1 plus C2 times ln x. So x to the power minus 1, C1 plus C2 times ln x, and x is positive. Okay, let's do another example. Y double prime. Uh, okay. Şöyle yapayım. 3x y prime plus 2y. Okay, now what is the equation now? It is r squared. So alpha equals 3 again, and beta is equal to 2. So we have alpha minus 1 r plus beta equals 0. So we get r squared plus 2r plus 2. Okay, well, this gives us what? R1 2 minus 2 plus minus b squared 4 minus 4 times this, which is 8 divided by 2. So it is minus 1 plus minus I. Okay, so lambda equals minus 1 and mu is 1. Therefore, what is the solution? So it is just e to the power, sorry, x to the power minus 1 and c1 times cosine mu is just 1 ln x plus c2 sine ln x. Okay, right? Mu is 1, therefore I have just ln x. And let me do one more example. So y double prime Okey. Şöyle yapayım. Ee, Şimdi r eksi 1 r artı 3 olsun. R kare eksi 2 artı 2r eksi 3. O zaman şöyle diyeyim. 3 y prime minus 3y equals 0. Okay. All right. So what is the characteristic equation? It is just, so here alpha is 3 and beta is minus 3. So we have r squared alpha minus 1 r plus beta. So from this we get r squared plus 2r minus 3, and this gives us r minus 1 r plus 3. So r1 is 1 and r2 is minus 3. So what are the solutions? C1 times x to the power r1, x to the power r1 plus C2 times x to the power r2. So it is just C1x plus C2 times minus x cubed. Okay. Yeah. Sorry. Well, if you choose e to the power minus t, uh, you mean this. Okay. Well, actually, we will come back to this again when we consider regular singular points. Actually, uh, you know, one should work with complex numbers, and there, the only actually thing we had to be careful about, x shouldn't be 0. But the thing is the following: since we have ln x, okay, uh, and so either you should put absolute value, but even in that case, when you consider complex numbers, ln z is not well defined. So one has to be careful. Therefore, just to be on the safe side, we usually put x to be positive. But actually, one can work with negative x values, and there you have to put this. But then of course you have also the following: suppose you have r1 equals 1 over 2, and when x is negative, then x to the power r1 means square root of x. So when x is negative, this is also something problematic. Okay, that's why we usually restrict ourselves to positive numbers. But actually, you are right. We may consider, negative x values, and actually, in general, uh, complex values for x. So not just positive x-axis, but all the complex numbers actually, except 0. But then you have to be careful. What do we mean by, for example, square root of minus 1? What do we mean by square root of I, and so on? Okay. Uh, since we don't want to, go into this kind of details, we just let x to be positive. Uh-huh. But you are right. I mean, actually, one may consider uh, not just positive numbers, but negative powers also. And actually, this would be enough, because if you choose t non-real numbers, right? For example, I times pi, then this is just -1, so x becomes negative. Okay. Okay. Any other questions so far? Okay. All right. Then let's continue with the next section, 5.6, series solutions near a regular singular point. Uh, part 1, actually, and 2, let's say part 2 also. So maybe I should make this 5.6 and 7. Okay, so this time I have px y double prime plus rx y prime plus qx y equals 0, and x0 is a regular singular point, regular singular point. In other words, px0 equals 0, but this limits exist. Limit as x goes to x0, x times x minus x0 times, sorry, I p q and r. Uh, qx divided by px. This limit exists, and we will call it alpha, and this limit exists. And we will call it beta. Okay. Well, you see, actually, Euler's equation is like this, right? Let me write as a remark. If you consider Euler's equation, x squared y double prime plus alpha x y prime plus beta y equals 0. So if I compare this with the with the above form, px is just x squared, qx is just alpha times x, and rx is the constant function, beta. They are all analytic functions. And you see, the only point which makes p 0 is just 0, right? x0 equals 0 is the only singular point of the equation. And so we may consider, ask whether it is regular or not. Is it regular? Well, let's check. So I look at limit as x goes to x0, x minus x0, qx over px. So this is just limit as x goes to 0, x times alpha x over x squared. Well, this limit is indeed alpha. And what about the other limit? Limit as x goes to x0, x minus x0, rx divided by px squared. Sorry. So this is limit as x goes to 0, x squared times beta divided by x squared. And this limit also exists, and it is beta. Hence, it is regular. Okay. I should write maybe is a regular singular point. Okay, now how about solutions? You know, okay. What about solutions around x0? Well, we will not do derivation for that. If you look at also the book doesn't give any derivation. The reason is that uh, actually this subject is much deeper than you know we would like to go in this course. Uh, if you wanna actually study how the solutions look like, how they can be obtained and so on, that's not an easy job. uh, that involves actually a careful study of this variable change. And although this looks like something simple, actually this is a very deep thing. This involves a lot of geometry and topology, and actually there are books about this subject, and we have a course called Math254, which I gave last semester. It is devoted to this kind of equations, okay, how the solutions obtained and so on. A whole semester book, okay, I mean course. So in general, uh, solutions, okay, obtaining solutions near regular singular points in full detail is quite complicated. Therefore, we will just uh, state a theorem describing solutions. Uh, okay, uh, we won't give any proofs. Okay, those who are interested in the subject may look at my okay, notes and videos of Math 424 class I gave in the spring of 2021. Bunlar benim web sayfamda var. Yani bütün ders bu tip işte çözümleri elde etmeye ve anlamaya yönelik. Özellikle son 5-6 derste bu diferansiyel denkleme geliyoruz. En baştaki yani dersin büyük çoğunluğu dediğim gibi topolojiye ayrılıyor. Yani bu buradaki işlemler, bu diferansiyel denklemler işte diferansiyel denklemlerin veya analizin işte konusu gibi gözükse de aslında işin içinde oldukça yoğun bir topoloji var. E, Ve o topolojinin yardımıyla aslında çözümler elde edilebiliyor. Yani başka türlü de elde edilebilir ama topolojik olarak bakarsanız büyük resmi çok daha iyi görüyorsunuz. Peki, şimdi ben söz verdiğim üzere size şey vereceğim, teoremi state edeceğim. O teorem bize çözümlerin nasıl olduğunu söylüyor. Ondan sonra da bir iki tane örnek yapacağım. Örnekte de maalesef e, çok fazla suya sabuna dokunmayan örnekler yapacağız. Çünkü yine belli durumlarda çözümü e, bütün genelliğiyle yazmak hiç de kolay değil. Peki, okay, now consider the following equation. So x squared y double prime plus, sorry, not x squared, I am sorry, px y prime y double prime plus qx y prime plus rx y. Let x0 be a regular singular point. Okay. The equation okay, let alpha and beta be the following limits. Nedir? İşte alfa şey, limit x sıfıra giderken x eksi x sıfır çarpı q bölü p'nin limiti and beta da yine x sıfıra giderken x eksi sıfırın karesi çarpı r bölü p'nin limiti. Okay. The equation, daha önce işte yazdığımız denklem r kare artı alfa eksi 1 r plus beta is called the indicial equation. Karakteristik denklem demiyoruz buna. Indicial equation of the differential equation for the regular singular point x0. Okay. Now we have three cases. So, okay, let R1, R2 be the roots of the equation of the indicial equation. Then we have the followings. Birinci durum şu. Okay. If R1 is R1, R2 are real and R1 minus R2 is positive, so we assume that they are distinct. R1 is the bigger root. The difference is positive, and uh, this difference is not an integer, then the solutions are as follows. Y1 is just x to the power R1, so here it means I may consider negative values also, and then I have 1 plus, so an times x to the power n, and y2 is x to the power r2 times 1 plus okay, and from 1 to infinity bn x to the power n. For some real numbers an and bn. Okay, so I have two series solutions as in the case of ordinary differential equations, but in front of this series solutions I have this, you know, x power terms, x to the power, you know, some numbers. In Euler's equation I have only these two. I had no power series, right? So in that sense this is just generalization of Euler's equation. In case these two again positive, but the difference is an integer. uh, okay, now first let me consider the case R1, R2 uh, both real. Then Y1 has the same form, but Y2 has the following form. So this is just I have y1x, so I have this term multiplied with ln x plus x to the power again r1 times okay, bn x to the power n. Okay, and if the difference is for some again a and bn, if the difference is a positive integer, if r1 minus r2 is a positive integer, so I don't consider, for example, complex roots, okay? They are just real roots. They can be the same or different, but when they are different, I have again two cases. The difference can be an integer or non-integer. The non-integer case is kind of easy. The integer case, this one will be a bit complicated. So is a positive integer, then y1 is again the same, x to the power r1, 1 plus n from 1 to infinity an xn, and y2 second linearly independent solution. So these are the linearly independent solutions. They have the following form: some number times y1x times ln x plus x to the power r2, and here I have 1 plus from 1 to infinity again bn x to the power n. Okay, for some uh, a, an, and bn. Okay, I have now extra coefficient a here. Okay, let me stop at this point. In the second hour, I'll go over the theorem and then we will do some examples.